While studying the basics of both inorganic and organic chemistry in a course which is titled Anatomy and Physiology, we really do not aim to make better or ultimate knowledge that comes from the field of chemistry. We're really trying just to extract the moments that are important and that we can apply later on to a number of different processes that are pertinent for a human body, in particular, of course, that is the physiology. So, what I would prefer that we take a look together is going to be interesting from a perspective of understanding the composition of atom, and we would need to take a look at a couple of slides that are coming from your textbook, Tortora and Grabowski. So we're going to have here an idea of what an atom, as the smallest unit of matter, is made of. It is, of course, made of nucleus, within which we can have positively charged particles or protons, and heavy particles, but no electrical charge in them, and they're called neutrons. So protons and neutrons are those ones that are making the nucleus, and negatively charged particles, the electrons, are those ones which are orbiting at very fast speeds around the nucleus. So due to their speed of travel, sometimes we illustrate it in this form as the electron cloud model, understanding that within this blurred cloud, basically we have very fast moving electrons that are always matching the number of positively charged protons in the nucleus. But for a practical reason, I think that we are better off by seeing the electron shell model, which illustrates electrons as being stationary, but we can at least count them and to say if this chemical element is carbon with 6 protons within its nucleus, then the total number of electrons will have to be 6 as well. So that chemical element is electrically neutral. And this results now in another thing that we have to observe, that electrons cannot all fit into a single electron shell. They fit into multiple overlapping, like concentric circles, electron shells, where the closest one to nucleus may contain 1 or 2 electrons. And if it has 2, we would say it has gained its stability, so cannot accept the third electron to keep orbiting around the same shell. Therefore, we have to open up the second, third, and subsequent electron shells to fit other electrons, especially for the elements that have 20, 30, or maybe even 40 electrons that need to circulate around the orbit. So second electron shell can have up to 8 electrons, but once it gets filled with 8, it is essentially gaining stability to that chemical element, and it has less needs to keep stepping into different chemical reactions. So when the outermost electron shell is saturated, that chemical element really becomes a little bit harder to get forced into a chemical reaction. If it has less than 8, then it is very much eager to step into chemical reactions. And that's why in natural form, for example, you really don't have atoms of hydrogen. You would say, well, how come? Yeah, well, we have them, but most of them either make a molecule of 2 atoms of hydrogen connected to each other, or majority of hydrogen actually becomes bonded to oxygen to make molecules of water, and then we know about 2/3 of the surface of this planet is covered with water. So obviously that is preferred way for a number of chemical elements to exist, because in their atomic form they're unstable. In their molecular form they become much more stable. So let's take a look at this, which illustrates multiple chemical elements in atomic state and number of electron shells we need to see in order to fit all of their electrons. So hydrogen, being just with a 1 proton, making its nucleus, will certainly have just one electron orbiting around it. This single electron shell will be more stable if somehow we can manage to put another electron into it, so it will change the electrical charge. This would have two negative versus one positive. It will turn into hydrogen ion, but that ion is going to be practically part of the chemical molecule within which hydrogen would be fully saturated and would not have a need to step out from one stable molecule into another one to keep looking for something else over and over. Mass number, as you know, is the sum of all protons and neutrons within a nucleus. So here we obviously have just one proton, and that is equivalent of atomic mass of 1. But next chemical element in the periodic table is the helium, and its mass number is already 4, which means it has 2 protons and 2 neutrons, so nucleus is actually made of 4 heavy particles. So that means between first and the second element on the periodic table of elements, we already have a gap between 1 to 4, which could be filled up with naturally or sometimes in a laboratory setting established, sorry for a moment, the word just slipped my mind, isotopes of the same chemical element by having extra neutron added to the nucleus of hydrogen, or extra 2 neutrons, practically making them not hydrogen any longer, but chemical elements that are known as deuterium or tritium, and they are chemical elements that are used in the production of what is called the heavy water that is frequently used in the nuclear plants for cooling down the nuclear reactors, because water made of these hydrogen atoms is having certain thermal capacity to absorb the heat. Heavy water, being made of hydrogen atoms that have 2 or 1 neutron in its nucleus, has better heating capacity and will absorb the heat from a nuclear reactor. Carbon, made of 6 protons and of course 6 neutrons, 6 electrons, need to circle. First electron shell 2, second electron shell has 4. Nitrogen, with 7 protons in the nucleus, 7 electrons, 2 in the first, 5 in the second electron shell. Oxygen, with 8 protons, 8 electrons, of which first 2 are in the first electron shell, and then 6 more in the second electron shell. So what do we see here? The second electron shell can have up to 8, which means carbon misses 4 electrons until it becomes really part of the molecule, which has properly saturated its outermost electron shell with 8 electrons. Nitrogen needs only 3. High oxygen needs only 2. And that is one of the ideas that will come quite frequently, and we will have to address it also through a section of chemical bonding so that you understand a little bit better what these electrons and the need for complete fulfillment of the last outermost electron shell means. Here is the sodium, so you can see with 11 electrons we had to open up the third electron shell, 2, 8, and then 1. And here's a chlorine with 17 electrons, 2 plus 8 plus 7 in the third. What's the difference? Sodium is having only 1. If it manages somehow to donate that one, its outermost electron shell will be made of 8 electrons and it will be stable. Chlorine, on the other hand, does have the outermost electron shell made of 7. It needs only 1. And if somehow it can find it, its electron shell will become stable. So sodium obviously will be looking to donate that electron. Chlorine will be looking to receive that one. They will manage to do it. And that's why in the natural form, we do have crystals of table salt that are composed of sodium and the chlorine ions. So they cannot maintain their atomic status. When the sodium donates its electron, it has one positive charged particle more than what's the total number of electrons. So it becomes sodium with a single positive charge, that is the sodium ion. Upon receiving a single electron, the chlorine also will have one electron more than the total number of protons in its nucleus. So it will also become an ion, chlorine, with a single negative charge. And that kind of ionic nature of sodium and chlorine will be something that you and I will see in the next section about bonding of different chemical elements. Just to confirm, potassium with 19 protons in its nucleus, 2, 8. In the third shell, we have 8. The fourth one haven't been properly illustrated, so we're going to do something on our own. We're going to put here the 19th electron that should be in the fourth electron shell. So in certain sense, potassium is very similar chemical element to sodium due to its single electron in its outermost electron shell. Potassium looks to donate it, to give it away, and when it manages to do that, it will become positively charged ion of potassium. And iodine, which we can have here, is also quite similar to chlorine. The atom of chlorine had outermost shell within which we counted 7 electrons. Obviously, by adding one more, it'll make it stable. If you and I do the same thing for iodine, in its outermost shell, you and I can count also 7, so it will be missing one extra electron to make its outermost shell being stable, and for the same reason, it will also easily react with any other chemical elements capable of donating that kind of preferred electron. So I hope that this makes things a little bit easier, a little bit better to understand, and we will take a look at other things and we will see chemical bonding in a later part of this presentation. That would be all for today for this part. See you later on.